In this video, I will solve two examples to understand how to find a solution of non-homogeneous recurrence relation. Here, I repeat for new audience, those who are watching this video first time, on discrete mathematics is that we have a homogeneous part, then we have a non-homogeneous part in this recurrence relation. And in the previous video, we saw that there are two solutions for such kind of non-homogeneous recurrence relation. One is called the homogeneous part, and another one is the non-homogeneous part. So what I am saying is that the solution an of this non-homogeneous recurrence relation can be obtained when you get the solution of homogeneous part and then you get a solution of non-homogeneous part. Yes, this is a particular solution. So we try to find these two solution and then we get a solution of non-homogeneous recurrence relation. So first of all, to find the homogeneous solution, we need a homogeneous recurrence relation, which is given as from 1, we have an is equal to 3an minus 1. And we already know that the characteristic equation for this recurrence relation is r minus 3 is equal to 0. Let me just recap what was what was the characteristic equation. R square minus c1 r minus c2 is equal to 0. And if you have only the first degree recurrence relation, in this case it is 1, so then you have to write the r minus c1 equal to 0. That's how you write the characteristic equation. So we have r is equal to 3 as a root, and the solution for the homogeneous part is an homogeneous will be equal to some constants, which is alpha 1. You can call it c1, whatever the name you like. And then we have r raised to power n. And the solution is alpha 1, 3 raised to power n. So this is the solution of homogeneous part. Now the question is, how can we find the particular solution? And here you can see that in the equation 1, we have this f of n. Remember that whenever you have a system, and if that system contains as input some kind of polynomial, then the output will be a polynomial as well. If you have input as a sinusoidal wave, your output will also be sinusoidal wave. So here, if we have 2n, it means that we have um, a particular solution of the form which is written as Cn plus d. And we already know that this particular solution will satisfy the equation 1, which is non-homogeneous recurrence relation. How we know that this will satisfy the equation 1? We know that since in the previous video we saw the theorem which says that the particular solution will satisfy the non-homogeneous particular form and the homogeneous part will satisfy the homogeneous recurrence relation. If it satisfies the non-homogeneous recurrence relation, then we should put this equation number 3, which is a polynomial, into equation number 1, which is non-homogeneous recurrence relation. So we put that value on the left-hand side first, Cn plus d, and on the right-hand side we have 3 an minus 1. So an minus 1 is actually your p, the polynomial, which is actually a and p. You may call it a and p. It is up to you whatever notation you want to use. A n minus 1. So this whole is a n minus 1. So c n minus 1 plus d plus 2n. Okay. Now what we do, we multiply and solve these two equations. So this equation, so cn plus d, that will be equal to 3 cn minus c plus d plus 2n, and cn plus d equals to 3cn minus 3c plus 3d plus 2n. And after simplification, is there any problem over here? Let me see if I have some problem over here. No, I think everything is fine. So cn plus d minus 3cn plus 3c minus 3d minus 2n is equal to 0. So we can subtract these two minus 2d, and finally we combine the terms for n. When we combine the terms for n, we get 2 plus 2cn plus 2d minus 3c is equal to 0. And the theory says that the non-homogeneous solution should satisfy. It means that the left-hand side must be equal to 0. And this can only be equal to 0 when we have the coefficient of n equal to 0 and this constant term will be equal to 0. So when we have 2 plus 2c is equal to 0, 2d minus 3c is equal to 0, and after solving that we can get the solution, the values for c and d, and the c is equal to minus 1 and d is equal to minus 3 by 2. So the particular form was a and p is equal to pn, and that will be equal to minus n minus 3 by 2. And the final solution is an is equal to minus n minus 3 by 2 plus alpha. What was alpha? This is alpha 1, so it is alpha 1 3 raised to power n. So you can put the value for the initial condition. Initial condition is a1 is equal to 3. So we put n is equal to 1, a1 minus 1 minus 3 by 2 plus alpha 1, 3 raised to power 1 is 3, and this is equal to 3. After solving that, after solving this for alpha 1, we can get the solution. So this was the example 1, which says that you can find a non-homogeneous solution of non-homogeneous recurrence relation. Now the next example, although the video is a bit longer, but we have to find the solution of second example as well. So here it has been asked to find the solution of this non-homogeneous recurrence relation. And first of all, let me just write the characteristic equation. Since it is a degree of 2, so r square, this is c1 minus 5r minus c1 is 6 is equal to 0. And when we solve that, the homogeneous an homogeneous will be equal to alpha 1 3 raised to power n, alpha 2 2 raised to power n. So r is equal to 3 and 2. So this is the homogeneous solution. So here f of n is 7 raised to power n, and the particular form will look like this. A n p will be equal to alpha 3 7 raised to power n. It is up to you, whatever the name you like to call this constant, c1, c2, c3, whatever. So when I put that a and p into the non-homogeneous recurrence relation, we put that value into this equation number 1. So an will be alpha 3 7 raised to power n. Since the output was like 7 raised to power n, the input was 7 raised to power n, the output will also be 7 raised to power n. So this is equal to 5 alpha 3 7 raised to power n minus 1, 6 alpha 3 7 raised to power n minus 2 plus 7 raised to power n. Uh, here, here I have just put the values for the non-home particular solution into the equation 1. And after solving that, we have alpha 3 that is equal to 1 over 1 minus 5 over 7 plus 6 over 49. And we have 49 over 20. So the final solution an, that will be equal to homogeneous part. Homogeneous part is alpha 1 3 raised to power n and alpha 2 2 raised to power n plus 49 divided by 27 raised to power n. So this is the final solution. Thank you for watching.